All right, so I was asked to give a little bit of more of an advanced tutorial. So I will not go into the standard stuff of Scikit-Learn, how to build a model that much. I want to do a quick review of that, and then go into some more advanced specialized things. So I put up some material online with some notebooks. If you want to follow along, the slides, at least as an open office presentation, are also online. But it's mostly going to be slides this time, actually. And sorry, I'm still a bit jet-lagged. Also, I have metal staples in my head that don't help my concentration. So a little bit about myself. So I did a PhD at the University of Bonn in machine learning, computer vision. Then I went to Amazon Machine Learning, where I did computer vision applications and forecasting. And now I'm at the NYU Center for Data Science, where I work on Scikit-Learn more or less full-time. So as you all, please feel free to interrupt me at any point. So the idea is that you learn something about Scikit-Learn. So if something I'm saying is unclear, please interrupt me. So Scikit-Learn, as you probably know, is a machine learning library in Python that has a lot of algorithms for different machine learning tasks like classification, regression, clustering, and so on. But it additionally has stuff to do model selection, grid search and cross-validation, model evaluation things, and a lot of and pipelining features, pre-processing to build whole modeling pipelines. It's a pretty big open source community around Scikit-Learn. So there's around like 20 core developers, depending on how you count. There's, for each release, between 100 and 150 people contribute. Pretty much, I'm pretty sure some of them are in the room for the last release.
You're my favorite.
Oh. All right. So so here's what I'm going to talk about in this advanced tutorial. So first, basic concepts, working with text data, then more advanced model building and evaluation, out-of-core learning, which will touch on some of the stuff that I talked about yesterday. Who in this room was at the meetup yesterday? Not that many. Okay, so it's not too bad. And then new stuff in 0.17, which is the current stable release, and 0.18 def, which will be the next release in the next month or 2 months, I don't know. All right, so maybe just sort of for me to calibrate, how many people here have used Scikit-Learn? Okay, how many people here have not used Scikit-Learn? Huh. So I was asked to do an advanced tutorial. Sorry for the people that have not used Scikit-Learn. Things might be a little bit too quick, but I try to cover the basic principles. So whether you follow along or not, it's always good to look at the documentation. We have a lot of documentation, particularly on scikit-learn.org. In particular, what I find most helpful is the user guide, which has narrative, like explaining all the algorithms and how they work, and an API documentation, which explains what all the different parameters are and what all the functions are and so on. So user guide gives a little bit more of a big picture, and API gives all the details of the implementations. There's also examples, which are also helpful, I think. So obviously, to do machine learning, we need some data. The way we represent data for Scikit-Learn is as a two-dimensional NumPy array or SciPy sparse matrix. And so for all of this talk, I assume everything is numeric. And that's the interface that most of Scikit-Learn has. So you have floating point numbers. Each sample is one row in your two-dimensional array, and each feature, one particular property is one column. So let's say each row is one user for which you want to predict whether they click on something, and one column is, I don't know, their age or gender or whatever. And then you have some output, which are, if you do supervised learning, which are for classification, discrete labels, or for regression, like continuous values. And I'll always call these X is a two-dimensional data array, and Y is a one-dimensional array of targets. And I will always use these letters. So then to do like basic supervised learning, all the machine learning algorithms in Scikit-Learn, whether supervised or unsupervised, are all implemented in Python classes. So what you do to use any algorithm is you instantiate a class that's, say, a random forest classifier here. This CLF object has the methods to build the model, to apply the model, and all the parameters of the model, everything that's estimated from the data will be stored in a CLF object. So this encapsulates the whole model and how it is applied. You build all the models using the fit function. So I give the fit function my training data xtrain and the desired training outputs ytrain. This would be for classification or regression. And they build a model, here the random forest, and store them in the CLF object. If I want to use the model to predict, I call clf.predict with the test data, the two-dimensional array of the test features, and I get back one-dimensional array of responses. If I want to evaluate the model, I can use the score method, which gets both the test data and some test labels. This tells me how well my model generalizes to the test data. And this basic API is the same for all classification and all regression algorithms. And they all have this fit predict methods. What scoring does is basically it makes a prediction, and for classification, it computes the accuracy, so how many of the predicted labels are the same as the test labels, and for regression, it uses the R-squared. Any questions so far? Okay. The other big class of models that are very commonly used, I think, is unsupervised transformations. These are models that create a new representation of the data. One of the most classical one of these is PCA, Principal Component Analysis. So here I want to make a model that creates the first three principal components. I have PCAs implemented in a class. The time to set any of the parameters of the model is when I instantiate it. So now I have this PCA object, which is an instance of the PCA class, where I set the components to 3. So extract the 3 first principal components. Then again, I have a fit method, which takes the data array xtrain. This is an unsupervised model, so there's no ytrain. Or even if there was, we would not use it. So this stores the model, so the coefficients of the first 3 principal components. Then I can apply this model to some new data xtest, and then I can use the transform method to get a new representation of the data. So here, transform projects the data on the first 3 principal components. So here's a summary of basically most things that are important of the basic API of Scikit-Learn. So all the models have a fit function, or fit method, sorry, where the first parameter is the data x, the training data. And if it's a supervised model, there's also training labels or training targets y. There's a predict function if you want to predict something like the y. This is for regression classification and also for clustering, where you want to get cluster labels. And there's a transform you use a transform method if you want to get a new representation of the data. So you transform your data x into a new x. This is for preprocessing, dimensionality reduction, feature selection, and feature extraction. Is that all right so far? All right.
Can you clarify the difference between selection and extraction of features?
Selection means I choose a subset. Extraction means I create new features from the old. So, for example, it's most commonly used when you have non-numeric data, like you have images and you want to have key points, or what we're going to talk about later, you have texts and you want to have a backward representation. So feature extraction is going from your raw data to like the numeric representation that we want to work with. All right, so the next thing I want to talk about, which is like essential to all machine learning, is model complexity, or like the concept of model complexity, which is also called the bias variance trade-off. I really don't like the word bias variance, like the term bias variance trade-off, and I can explain in a bit why not. I wish I made that joke. model complexity or overfitting, underfitting. So who has heard of overfitting here? Everybody, okay, cool. I'm still gonna explain it again. So most machine learning models have some tuning parameter that say how complex of a model I want to learn. For example, in linear models, you have some L1 or L2 regularization. In decision trees, you can decide how deep do I want to grow the tree, and something like that exists basically in all models. And so if you go from simple models, which is on the left, to complex models that's on the right, how accurate you can predict on the training set goes higher and higher, because more complex models mean you can model the data better and better, and so you can make better and better predictions. However, if you look at what happens on the test set on generalization on new unseen data, the accuracy rises with more complex models, but then there's some tipping point where generalization gets worse. And this is sort of where overfitting happens. You build a model that now fits to the noise in the training data, focuses too much on the very particularities of the training data, and learns something that will not generalize to the new data. And so there's a sweet spot in the middle that we want to find, and sort of if you're on the left-hand side of the figure, you're the underfitting regime. Your model is too simple. And you can usually see that by seeing that training and test accuracy are very similar. If you do as well on the test set as on a training set, that probably means your model is too simple. You should do a little bit better on the training set. If you do a lot better on a training set than on a test set, that probably means you're overfitting, because you don't want the gap to widen too much. And so selecting the right model and selecting the right parameters of the model is what we do to find the sweet spot. And so now I want to talk a little bit about the methods that we use to find a sweet spot. So the first thing we can use is cross-validation, just to evaluate where are we on this curve. So you can do split your data into training and a test set, training on a training set, test on a test set. That will give you some measure of how well you generalize. But it's not a very robust measure. So a lot of people want to do cross-validation, so you split your data into k-folds, let's say 5, train on 4, predict on the other one, and repeat this 5 times. It's very simple to do this in Scikit-Learn using the cross-val score. It's one of the very few actual functions that are not classes in Scikit-Learn. And so you call the cross-val score function with the model you want to evaluate as the first parameter. So here it's a support vector machine, the data x, the labels y, and then some cross-validation method. So here I just say 5-fold cross-validation. So what this does is it does the splitting, it does 5 iterations, and it returns the scores. If I say CV equal to 5, they will actually do stratified cross-validation for classification by default. So if there's a SVC, support vector classifier, this is a classification task. And so this will do stratified cross-validation, which means it preserves the fraction of each class in each fold. So if overall I have 90% in class A, 10% in class B, then this will make sure that in each fold there's 90% of class A and 10% of class B, which gives you a bit more robust estimates. There's also other kind of cross-validation methods. Apart from k-fold and certified k-fold, there's shuffled split, which splits the data randomly, and you can control the number of iterations and test size independently. There's also things that work with correlated groups. For example, if you have data coming from several patients and you want to generalize from one patient to the other patients, or from one website to the other websites, is called label k-fold. And there's 10 of them in Scikit-Learn. And it's also quite easy to create these yourself. If you have a particular correlation structure in your data, you need to make sure that you respect the correlation structure when you do cross-validation. For example, I should have an image for this, but if you have a time series and there's a trend in the time series, now if you do k-fold cross-validation with shuffled data, you will have completely destroyed the trend. So this means you will have points that are close everywhere. So your training set will cover each area of the trend. Whereas in reality, sort of, you want to usually predict from the past to the future. And so you will not see the last part of the trend going up. So if you have time series or other correlated data, it's very important that you have a cross-validation method that respects these correlations and actually reflects how it will be used in production. Oh yeah, leave one, like these label one are the ones that work with correlated groups. Okay, so cross-validation helps us to evaluate the model, but usually we don't only want to evaluate it, we want to find a sweet spot. And the way we do this is using grid search. Most of the models have like a whole bunch of parameters. Here, for example, the support vector classifier has regularization C, the type of kernel, and then like 5 different parameters for the kernel. And so we don't want to tune them by hand, we want to use grid search to find a sweet spot. The way I usually want to try to run grid search, or the way I usually run a grid search is I start with my whole data set, and I split it into a training and a test set. Then I run cross-validation on the training set and do grid search here. So for each parameter setting that I want to try, I run cross-validation on a training set and record the cross-validation score. Then I use the parameter setting that does best on the in the cross-validation and use this parameter setting for the final evaluation on the test set. So you can see here there's sort of a nested scheme. I split my data twice, basically. You could also do this by splitting your data in a training, validation, and test set. The crucial part is that you don't use your test set to adjust the parameters of your model. Imagine you have many, many parameters, and you adjust them all in the test set. Then maybe you have a good result just by chance. If you take the best of these results, you'll be way too optimistic in how well you actually generalize. So you actually should use your test set only exactly once. So maybe if you did some competitions on Kaggle and you submitted a lot of results and your leaderboard score went higher and higher and higher, and you said, oh, my leaderboard score is getting better and better, and then there was the private leaderboard and you were like 100 places below because you tested too many different parameter settings on the public leaderboard. This is the same principle. So we want to only use the test set. This is like the private leaderboard. Basically, we want to use this exactly once. All right. So the way to implement grid search with cross-validation in Scikit-Learn is pretty simple. It's implemented in the grid search class. So as I said before, I split off a test set before I run the grid search so I can evaluate the parameter setting. I define a param grid, which is a dictionary that goes from the parameters I want to adjust to the values I want to try. So here, this is like a logarithmic or exponential grid. So this goes from 0.001, 0.01, 0.11, 10, and not 100. So C and gamma are the parameters of the support vector classifier. So these are actually the parameter names that I want to adjust. And so I instantiate this grid search with the classifier and the param grid. The cool thing about grid search CV is it's what we call a meta estimator. So it behaves exactly like the classifier would. So it has this fit, predict, and score that we saw before. And so it has exactly the same interface. The only difference is that it uses SVC internally and then finds the best parameters. So basically, you can totally forget about it. You do grid search and just treat this grid as just another classifier. But when you call fit, what it does is it does run the grid search and it finds the best parameter set. Then it rebuilds the model using the best found parameters on the whole training set. And then you can use the test set to evaluate. And this will give you like an unbiased estimate of how well this classifier will do on new data. Oops. All right.
When you rebuild the model, do you use the validation set as well?
There is no validation set in the sense. I mean, there's many validation sets because I do cross-validation, right? And so this is like, I use all the data that I have. Any other questions about this? Oh, yeah, sorry. So you do use cross-validation on a training set. So this is relatively robust. So yes, you assume that sort of it's the same for the test and a training set. The test and a training set. I mean, you generally assume that the training and test data have the same distribution. Otherwise, you can't do machine learning. But sort of, you try to do this cross-validation to not only focus how good the training error is, you look at what is the holdout error on the training set using cross-validation, and then you basically confirm how well does this actually generalize to new data on the test set. Does this answer the question? Kind of. Or can you clarify maybe? Okay, so the question is, if you get the best parameter setting, why would it be the best one also for the test set? Because you assume your data is IID. So your data is independent, identically distributed. So all of Scikit-Learn and 99% of machine learning makes this assumption. And if you don't make the assumption that your training and your test data comes from the same distribution, you cannot learn anything. Unless you know how the distributions relate to each other. Any other questions? Okay, cool. So I want to go through a quick application, sentiment analysis. So this will be on the IMDb movie review dataset. So we have texts here, which are reviews of movies like this one. One of the worst movies I've ever rented. Sorry, had one of my favorite actors on it, Travolta, in a nonsense role, and so on. And so we have a label for this, which is negative. So on IMDb, you have 1, 2, 3, 4, 5 stars. Here, we only want to classify the data into positive and negative. So negative is 1 and 2 stars, positive is 4 and 5 stars, and we threw away 3 stars because we didn't know what to do with it. Or the researchers that assembled this data set did that. And so the idea is, given a new movie review, can we predict, is this a positive review or a negative review? And we have a data set of 12,500 positive reviews, 12,500 negative reviews, and the same for the test set. So obvious problem here is this review doesn't look at all like the X that I wanted before. I wanted a matrix like with fixed number floating point values to represent my each sample. Here, each sample is like an arbitrary length free text. The standard method to go from free text representation to numeric representation that machine learning can work with is the back of word method. Who here knows the back of word method? Oh, okay. So this is implemented in the count vectorizer and the TF-IDF vectorizer in Scikit-Learn. So the basic idea is you start with some string that you want to encode. So let's say my review is this is how you get ants. The first step is to break it up into tokens or words. There's like several fancy ways to do this. In Scikit-Learn, use a very simple one. We basically split up by white space. So we have our sentence, we split it up by white space, we also lowercase it to normalize it a little bit. Then you go over your whole data set, over your whole corpus, say all the reviews we saw in the whole training set, and we build a vocabulary. This is basically a large dictionary of English words. So it starts from artwork to Zisk. And this is like usually in the tens, hundreds of thousands, depending on the data set size. Then we go back to the original string that we want to encode, and we count how often does each of these tokens appear. Out of these hundreds of thousands of words, only 6 actually appear. So there's a whole bunch of zeros and 6 entries of 1. So there's a 1 for ants, a 1 for get, a 1 for how, and so on. Because we don't want to store all these zeros, we use sparse matrix representation to only store the non-zero entries. And now we have a fixed length vector representation of integers. Most of them are 0, and we can use machine learning on these. Questions on that?
Yeah. Why don't you make singular from plural like ants? Like why don't you make it singular like ant?
You can make it singular. That's a bit more tricky. And also maybe you don't want to. I mean, you can also do stemming to get like different verb forms and so on. And
It will drastically reduce the complexity of the problem. So if you like stem it. Yeah?
Maybe. I mean, okay, using a Porter stemmer nearly always increases performance. I don't do this here, for simplicity's sake, let's say. You can use more advanced stuff with Scikit-Learn. You can give it your own tokenizer. So if you want to add even more complexity than we already had, you can consider not only single words, but pairs of words. So often you have something like good and not good. And if you only count how many, how often each word appears, the negation of the good gets lost. And you only count, oh, there's one good. And the not might be in a completely different, like, you don't care where the not is. So instead of looking only at single tokens, you can look at pairs of tokens, basically. So you look at all 2 neighboring words. So here, what I get out is, this is how you get ants. And you can do this if you want till arbitrary length. Usually, 2 or 3 makes sense. More, the feature space explodes. I mean, this is more or less, maybe not quadratic, but nearly quadratic increase in number of features. All right, so we have back of word, which we can do unigrams and bigrams. And this is how we're going to represent our data. So I'm going to switch to a notebook working with text data. Can you see this in the back? Yes? Okay. So there's the URL if you want to download the data. I actually didn't put the data in the repository if you downloaded it, because on the last conference, everybody tried to load this 500 megabyte data set at the same time, and then no one could check out anything anymore. So there's like a load files function at Scikit-Learn that loads, helps you load text data. And so here I have text train, which is just a list of strings, and Y train, which is a NumPy array. So Y train has 12,500 zeros and 12,500 ones. So these are the positive and negative labels. So 0 is negative, I think. Let's check this. And I also load the test data set, and that's the same size. I can look at, so this is test train, like it's the second training point. And okay, you can see this text. There's some Unicode in there. And you can look at the label. Here's 0, which means bad review. So words can't describe how bad this movie is. This is probably negative review. All right, so now we can use the count vectorizer to convert this data from the raw strings to the backward representation. So the count vectorizer, as I said, this is what I would call feature extraction. The count vectorizer is a transformer. So I fit the model using the data, and then I can transform it to a new representation. Here I instantiated the model, I fit it on training data, And now I check out how large is the vocabulary. It's 75,000 words. I can also look at, with get feature names, I can look at what kind of words it found. So it found a lot of, if I look at the first 50, that's mostly numbers and 1 p.m. and 0 a.m. And I don't know, maybe not super interesting. If I look a little bit later, then I see a lot of words starting with pin. Now I can, as I said, I can use the transform method. Now I get a sparse matrix representation, and there's going to be one row for each sample. So there's 25,000 samples and one column for each word, counting how often it appears. So there's 75,000 columns. And I can look at, so I picked out one training sample that's kind of short, and I can look out where there's non-zeros in this row in the matrix, and if you want, you can figure out sort of the correspondence of these non-zero entries to the words. I can also transform a test set in the same way, and now I have these two sparse matrix representations, and I can just learn a classifier. So here, linear SVC, linear support vector machine, standard linear classifier, I call fit on the training set and training data and training labels. I can look at how well it does on the training data and the training labels. So you can see I do basically perfectly on the training set and about 84% correct on a test set. So there's like a bit of a gap, and doing basically perfectly on a training set probably means my model is a bit too complex. I built a function here to visualize what the model learned. I picked out the, maybe can I zoom here? Oh, does anyone remember how to zoom out? Sorry. Maybe like this. So I picked the 25 largest and smallest coefficients in the linear model, and you can look at, so red are the 25 smallest coefficients, so they correspond to being indicative of negative reviews, and you can see disappointments, worst waste, poorly, unfunny. But then you also see things like crow, Britney, doy, screens, which are slightly odd maybe, depending on your opinion of Britney Spears, maybe. And then if you look at the most indicative of a positive review, you see scariest, refreshing, reeling, appreciated. But then also things like Carrie, Australia, squirrel. So, I mean, these kind of make sense, but maybe not perfectly. And that's probably like a case of overfitting, where we fit too strongly to the training set. I set the C parameter somewhat differently here. So much smaller, that's much stronger regularization. And I can look at the score and the coefficients again. So the score went up from 84.5 to 88. So the test set score improved a bit. And now also the coefficients make more sense. So I have worst, waste, awful, boring, poor, poorly. So maybe I should also prune poorly to poor. And disappointing and disappointment. And then the good ones are like excellent, perfect, wonderful, great, amazing, favored, loved. And yeah?
Why did you choose that parameter? Why did you choose that parameter?
So the question is, why did I choose this value of the parameter? Okay, so I did the worst thing, thing I told you not to do, which is I tested on the test set. So that was my first mistake. And so what I should have done is do grid search over C. I can guess this though, because so the linear support vector machine only has a single parameter C, which is just a regularization. By default, it's 1, and I wanted more regularization, which means I need to decrease C. So decreasing C to like 0.1 or 0.01 or 0.001 would be like the first thing I try. I tried a bunch and this worked well. I should have done at least a split into test, validation, training, validation, and test, but I didn't to keep it a little bit simpler. All right. So far, so good. Or any other questions? All right. So what we saw here is a pretty simple example of a standard pipeline where you have some raw data, you do some feature extraction, and then you do some supervised model. And because this happens so often, there's something in Scikit-Learn to help you with building these processing steps, which is called pipelines. So yeah, as I said, so usually you don't get training data the way that you want to feed it into your model. You do things like feature extraction, scaling, and feature selection before you pass your data actually into the model. And one particular problem with these more complex pipelines is that often people then do cross-validation and grid search only on the final model, which is pretty bad because it means that all the previous steps saw all the data. So if you do cross-validation only in the last step, the previous steps all saw the test fold. And so you will get too optimistic results. That can be very off. So what you definitely need to do is to do cross-validation in the most outer loop and cross-validate everything that happens after you get your data. And pipelines also helps you with that. So what pipelines basically does is it chains several transformations. So here I have T1 and T2, and then optionally I can have in the end a supervised model, or I could have a clustering model or whatever. I mean, classification regression is the most common. So when you fit this pipeline, what happens is you get your input data X, your labels Y, you fit the first step T1, and you call T1.fit. Then you build the first transformation. Then you call T1.transform to get the new representation of the data X1. Use X1 to fit X2, transform the data, use X1 to fit T2, then you transform your data using T2 to get X2, and then you give X2 to the final classifier. In what we saw before, X was the strings, T1 was a count vectorizer, and then we built a sparse matrix representation and gave it to the classifier. In pipelines, you can have arbitrarily many of these steps. And in prediction, you just use all of the transformers to transform your input data and then do a predict on the last step. So to go back to our text example, so here's a pipeline that does both the vectorization using count vectorizer and the classification using a linear SVC. So there's this helper function make pipeline, just gets the list of transformer and the classifier. This again is what I call the meta estimator, so it behaves just like a classifier. So it has a fit, score, and predict methods. And now what I can do is I can give this to grid search and, for example, actually properly adjust the parameter C. Grid search with pipelines works basically the same as with any other classifier, though you have to specify in which step of the pipeline you want to adjust your parameter. Here, I want to tune the parameter of the linear SVC. So I have to prefix the parameter C with the name of this step in the pipeline. By default, everything is named by the lowercase class name. So this is the name of the step. Then there's a double underscore, which is just a separator. So that's you always need to use a double underscore when you want to grid search pipelines. And then the parameter C. And I was pretty sure I used a different version of Scikit-Learn. Never mind. Yeah, disregard the warning. And then you can get best params, or you can use the grid search to make predictions. Often you want to then inspect the steps of your pipeline. So what I did here, I want to visualize the coefficients again. So in the grid search, you can go to the best estimator. So the best estimator is the model that was built on the whole data set using the best found parameters. Usually, so if you only want to predict or score, you don't need to access this. You can do predict and score and fit on the grid. But if you want to actually inspect what's going on, you can look at this best estimator. And this best estimator is now the pipeline with the best set parameter. And now I can look at the steps of the pipeline. So here, there's the named stats attribute in the pipeline. And so I look at the linear SVC step, and I look at the count vectorizer step. And so I get the feature names from the count vectorizer and the coefficients from the model. And that takes a little bit. Why does it take so long? So one of the things that's happening here is, so this will build a new vocabulary for each split of the data set into training and or for each iteration of the cross-validation to make sure that the training and test parts are always separated, and which is why this takes a little bit longer. We can then also search over parameters of the preprocessing, for example. So here I look at, should I use only unigrams, or should I use unigrams and bigrams? So this is a parameter of the count vectorizer, which is called n-gram range. N-gram range is the tuple minimum range of tokens I want to look at, maximum number of tokens I want to look at. So either I just look at tokens of length 1, or I look at tokens look at single tokens and pairs of tokens. And so I grid search both the C and this. And all right, this will run for a bit, but so questions about grid searching with pipelines or pipelines in general?
Can you actually make not one pipeline but many pipelines and then compare the performance of them in one shot?
You mean?
For example,
grid searched several pipelines, basically, or?
No, I'm just wondering, like you said that every action of your data processing should be cross-validated as well as the model itself. So that means that if you change your steps, you would like to compare how like the new step good compared to the previous one. So for example, you did like some kind of transformation of the data, like logarithmic transformation. Then you say, maybe it's not logarithmic, but let's do other transformation. And then you want to validate them together, like to see how they're different in performance. So can you do it in one shot, or you need to create different pipelines and then basically visually compare the results?
Currently the second, hopefully soon the first. So we want to be able to search over different steps in the pipeline, but it's currently not possible. Okay, so let's see if both of them. Oh, no, the grid search didn't finish. That's too sad. But if you want to do stuff with text data like seriously, you should also look at NLTK, which is a natural language toolkit, and a new kind of replacement for it, which is called Spacey. Definitely check these out if you want to work with natural language data. So actually, I think I got it. So, okay, maybe I'm gonna ask you in a little bit what you want to hear because I have way too much material. So one thing that I want to talk about definitely is randomized parameter search. So in the grid search, maybe I wasn't very clear on this. You try all possible combinations of parameters, and you repeat this for each split of the data set. So if you have two parameters that each take 5 values, as I said with the support vector machine, and you do 5-fold cross-validation, so you have 25 combinations of the parameters, and you do 5 iterations over the data, so you have 125 models that you learn, which is already quite a bit. now, if you add another parameter with 5 values, you have 624 models that you learn. And so things are kind of getting tricky. So one alternative to exhaustively trying all possible combinations of parameters is randomized parameter search, which I want to talk about now. So randomized parameter search is actually, there's more to it than just sort of sampling some parameters. Here is a figure that I love from a paper by Bergström and Benjo about why randomized parameter search is awesome. So on the left, you see a grid search. So you have two parameters, the important parameter, which is on the x-axis, and the unimportant parameter, which is on the y-axis. And so the function you want to maximize is this green function, which is like accuracy. And the green function, it only depends on the important parameter. So you train 9 models here, you run cross-validation 9 times for these combinations of the 3 parameters, and so you tried out 3 different values of the important parameter. And you completely missed the optimum. Now with the randomized layout, you just sample from the important parameter, and you sample from the unimportant parameter. And the important parameter will have a different, because these are like continuous parameters, they will have a different value each time. And so you will actually, instead of having 3 values of the important parameter, you have 9 values of the important parameter. So you get, for the same computational cost, you get a much higher resolution on what the important parameter. So this works very well if you have a lot of parameters and you don't know which one of them are important. And often in machine learning, you don't know what is really important on this data set, particularly if you have complex pipelines. And so this randomized layout can really help. There's smarter ways I want to talk about in a bit, but this is really a competitive method, so this actually works quite well. And so other benefits are if you have continuous parameters, you don't need to choose a step size, or like how many different settings do you want to try. And it decouples the runtime from the search space size. So before, you tried each point. So depending on how fine the grid is and how many parameters I have, this gives me the number of runs I have to do. For the randomized layout, I can just say, I want to run it until like 5 in the afternoon, and then I'm going to stop it and take the optimum. And I will get something meaningful then. If I stop grid search at some point, I wouldn't have explored the whole space, and I won't get anything meaningful. And so the most important part is, if you add irrelevant parameters, it doesn't get slower. If you add like 5 irrelevant parameters to the grid search, it will be impossible to do. If you add 5 irrelevant parameters to the randomized search, it's still as fast. So that's kind of cool. Yeah, so okay, this is a slightly more complicated example than what I thought I had. But so before, basically, we had something like count vectorizer, n-gram range. We tried different parameters, and then we had linear SVC, and we tried different parameters. And now instead of trying these discrete values on the exponential grid, we give it an exponential distribution, and we sample from this. And it's really, like, for what I showed in the last figure to make sense, it's really important that you use a continuous distribution if your parameter is continuous. This is the exponential distribution, and it kind of models this logarithmic grid. And the way you use it is exactly the same as grid search CV, just called randomized search CV. You give it here, I give it a pipeline for my text data, and I give it the parameter distributions. So it can either be lists if I have discrete parameters, or I give it distributions. So this is xpon is from scipy.stats. There's also like all the other distributions, and it just uses the RVS function of these. And so it gives this dictionary from parameters to values, or from parameters to distributions, and then there's how many iterations I want to run. And the rest is just as in grid search. All right. Any questions about this?
So the fact that you use exponential, that is your domain knowledge. You
Yeah,
expect this parameter to...
So the question was, why do I use expon? Yes, this is domain knowledge. So you still need to have like a prior over what you expect the parameters to be. And if this is bad, then this can go bad.
Is there a solution to the problem? Like, let's say you have no domain knowledge.
If I have no domain knowledge, then I go 2 slides further. Is there any questions? Any other questions? Okay, no. So there's sort of the more fancy version of this, which is called Bayesian optimization for hyperparameter search. And so basically here what I show is a figure from, I think it's an experiment paper, where we use Gaussian processes to search over hyperparameters. So here, sort of, the black function is what we, the black function is what we want to optimize, and so we start sampling a point, and at this point we see what we have these 2 points where we try to parameter settings, and then we saw how good the model does with these parameter settings, and then we fit a Gaussian process to this, which is like the gray area that you see, and this models how high the value is, but also the uncertainty. And you can use the uncertainty to pick what is the next best point to try. And so sort of this green function at the bottom, I don't know if you can see if it's green, where it's called acquisition max. This is sort of the combination of uncertainty and knowing the function value tells you this is a good next point to try, and then you try this. And sort of this will give you a better model. It will decrease the uncertainty here. It will give you a better model of what the actual function is. And you can keep playing this game and like propose new parameter settings to try. This doesn't need a prior. Slight caveat though, Gaussian processes usually use stationary kernels, which means that if your thing is on a logarithmic scale, you need to search on a logarithmic thing, otherwise it won't work. But there's an extension of this to find out if your model should be on a logarithmic scale or an exponential scale or a linear scale, your parameter. And one of my students is implementing that right now. Yeah?
Doesn't this assume that the function is kind of continuous? Or the differences, so if you make small changes, it
Yes.
has small changes in the results?
Yes. The Gaussian process makes the assumption that it's continuous, and it works best for like continuous parameter settings.
But is that often the case?
Yes.
Yeah.
I mean, it's if you have discrete choices, then the GP can't really do much else than just try them out. But for the continuous parameters, this makes actually a lot of sense. Though, I mean, you can do this, but the randomized search actually is pretty competitive to this. The main downside of the randomized search is that you actually do need to know a good prior. So if we're lucky, we'll get this in 0.18, probably 0.19 is more likely. We'll see. So another thing that I want to talk about for parameter search is you can actually do more efficient parameter search for certain families of models. So because the cost of parameter search is so big, there's tricks for some you can use. So I don't know if you're familiar with RFE. RFE is recursive feature elimination. What it does is it tries to find the least important feature according to some model, and it eliminates that, and it does this recursively. So let's say I want to know, or So the way this works is it fits the logistic regression to a data set, and then it takes the coefficient of lowest magnitude and drops the feature according to this that's like unimportant, tries again on the new data set, drops the next feature as unimportant. Then you can ask yourself, okay, how many features should I keep? And you can run grid search to see how many features you should keep. And so if I do this here, it'll iterate over all the parameter settings. So I do n features to select. Let's say I start with n features -1. So it fits the logistic regression, drops one feature, fits the logistic regression again, and scores it. Then I do n features to keep n-2. It fits the logistic regression with all features, drops the least important one, fits the logistic regression again, drops the least important, and fits the logistic regression again, and scores. And clearly there's like a lot of repetitive work. Doing things up to n features -2 helps you to do it to n features -3. So, I mean, you can just go on doing it. You don't need to start from the beginning every time. And so doing grid search like this is like super wasteful. So, yeah, don't do this. Instead, there's an object called RFECV, which has built-in cross-validation. And this just, does this for you. So it knows about the model, and it knows the logic about how the models are built as a function of these parameter and features, and so it just scans through all possible and features to keep, and and features to select, and it selects the best value without any repetitive work. And so this principle can be applied to a lot of models where different parameter settings can benefit from each other. One very prominent example is the lasso algorithm for L1 regularized linear regression, where so what you see here is this axis here is more or less sort of regularization strength or alpha. It's scaled a bit differently, but the y-axis is just magnitude of a coefficient, and each color encodes a coefficient. So if you have a lot of regularization, it's on the very left. You only have like all your coefficients are 0. If you start increasing the regularization, the red coefficient becomes non-zero. Then if you start decreasing regularization, the green coefficients becomes non-zero, and so on. So searching, and the nice thing about lasso is that these parts are all linear, and you can compute where the next step is. So here you can compute the model and also the score of the model for all possible settings of the regularization parameter all at once very efficiently. And so you can use the lasso CV object to do this for you instead of doing grid search and building a new model over and over again. And we have these CV objects for many models now, which allow you to search over one or multiple parameters very efficiently. Oh yeah, here's the list. So linear models, we have logistic regression CV, rich classifier, last CV, elastic net CV, lasso large CV, lasso CV, and so on. For feature selection, there's RFE CV. And for tree-based models, we actually have none currently, but we're going to have gradient boosting classifier CV very soon, which basically selects how many trees to add, because you can iteratively add more and more trees and check how well your model does.
Is that in 0.18?
Which one?
The gradient boosting.
I haven't reviewed it yet. So one of my students wrote it. I think it's done, but I haven't reviewed it yet. Oh, actually, no, we're not going to do a notebook for this. But the main downside here is these don't combine well with grid search. So if you put them in a pipeline and you want to put the pipeline in a grid search, that's bad. And it doesn't really work right now, because then the grid search will do a cross-validation, and this object will do cross-validation again. Then you have nested cross-validation that you don't want to do. And I hope to fix that soon. But so these are awesome if you use them on by themselves. If you put them into pipelines, things get weird, and you should be aware and think about what's happening then. All right. we don't have that much time anymore. Are you more interested in how to use different evaluation metrics, which is one possibility, how to do out-of-core learning? These are actually the two only ones. Out of core? Okay. The loudest people win. There's cool scoring functions. Okay. There's a notebook on how to use scoring functions. You can look at it. So out-of-core learning. Out-of-core learning is doing learning with data that does not fit into RAM. So I like to think about 3 different scales for data. Oh, actually this is, no. So I want data that fits into RAM, data that doesn't fit into RAM but fits on disk, and data that doesn't fit on a single machine. And so data that fits into RAM is sort of on my old laptop, so this is actually my new laptop. So my other laptop has 4 GB of RAM, which is 1 million data points with 1,000 features. That's already quite big, and I can learn on this in my old laptop. And if you get an EC2 machine from Amazon, you can work on 68 million data points with 1,000 features and fit them all into RAM. So who has more than 68 million data points in this room? Okay, so you don't need out-of-core learning. You just need to spend $3.12 per hour, and you can fit your data into RAM, and you don't need to do out-of-core learning. And that's actually, it's going to be much faster, and it's much cheaper than hiring a back-end engineer. You don't get a good back-end engineer for $3.12 an hour. Even if you have more data, you can still fit it onto disk, and for $7.50 an hour, you can get 6 terabyte of RAM in SSD drives. And so, if you only need a cluster if you have more than 6 terabyte of data. So, but I can still tell you how to do out-of-core learning. So if you only have 4 GB of RAM and you want to work on a large data set with your laptop, because maybe you're not allowed to use cloud computing because of data privacy issues or something like that. So the way to do out-of-core learning in Scikit-Learn is relatively simple. There's a function called partial fit that some of the models have. What partial fit does is you iterate over the data, and it continuously improves your model. If you call the fit function on any model in Scikit-Learn, every time you call the fit function, it'll forget everything it ever learned before. So you can call the fit function on Iris, and then you can call the fit function on ImageNet, and it'll be fine. But partial fit means that you feed in data, and you continuously improve the model. So, for example, you can load chunks of data from your hard disk, or you can stream it in over network. You need to basically write your own for loop, and with each batch of the data, you call partial fit. And then in the end, you get out a model. So the supported algorithms currently are SGD classifier, SGD regressor, perceptron, all these linear models, naive Bayes models, mini-batch k-means, incremental PCA, mini-batch dictionary learning, multi-layer perceptron in the dev runs, not in the release yet, and all the scalars like min-max scalar and standard scalar and so on. And the way this code looks like could be something like this. So here I instantiate my classifier, a linear classifier, and I assume I have like 10 batches of data, and I chunked them in a way that each batch fits into memory. So I load the data X batch and Y batch from some pickle, and then I can call partial fit on this batch. I also need to specify what the classes are so the model can allocate the right coefficients. So here this is like the digits data set, and I have 10 classes from 0 to 9. And so I iterate over the first 9 batches, and then I can evaluate on the 10th, for example. For many of the models, you want to go over the data set multiple times. So SGD classifier is a stochastic gradient descent. So after you iterate over a data set only once, you probably haven't converged yet. So you want to basically do another outer loop to improve the model further. The only model where you don't need this outer loop is naive Bayes. Naive Bayes basically just counts, and going over the data set once will give you the optimum solution. Oh, one thing that I haven't included here is there's a very helpful function or option in pandas. The CSV reader has a chunk size parameter which allows you to read very large CSV files in chunks, so that even if you have a CSV file that doesn't fit into memory, you can read parts of it and iterate over the parts. One thing that's also very helpful for working with large text data sets is the hashing trick. So before we talked about the text classification using Becker words. If you remember, you get your string, you tokenize it, you build a vocabulary, you do sparse matrix encoding using the vocabulary. If you want to do out-of-core learning, this part is a problem. For example, if you have streaming data, you can't go over the data set to build a vocabulary. And if you do out-of-core learning, maybe the vocabulary is so large that you can't store it in memory. But you can use the hashing trick to kind of avoid this problem. Here, basically, you replace this dictionary of all the words that you saw with just a hashing function. And you use each of the tokens and you hash it. And this hash gives you an integer. You limit it by doing mod with some large number. And then you use this integer as an index into the sparse matrix and put a 1 there for each of the words that you observe. So here, this appears, so I apply my hash function to this, I get out 832,412. That means I put, or I add a 1 in the feature representation at position 832,412. And this way, I don't need to build a vocabulary, and I can just stream data, and I can encode the data without ever seeing or knowing beforehand all the words. This has two, or maybe one main drawback. The main drawback is you can't go back from this to the words. So if you built a linear model on this before we plotted like, oh, this coefficient means this word, and that makes sense. But because it's a hash, basically, you cannot go back to the words. So you get a large feature vector, and you have no idea what it means. Because it's hashing, you can also get collisions, so two words can hash to the same value, so they can correspond to the same feature. But it's very unlikely that two words that are both important for your task hash to the same value, so that's usually not a problem. I think, wait, how much time do I have? 10 minutes. Okay, I think I'm gonna skip kernel approximations and I'm gonna go to new stuff in Scikit-Learn. Oh. Okay, we have even, okay. 5 minutes, great. I also have stuff in this, how to build your own estimator, that someone asked me to add yesterday, and then I added it last night, but I can't do it. Okay, so what's new in 0.17? 0.17 came out last summer. And if you haven't caught up with it, here's what's new. Latent dirichlet allocation, which is a topic model, it's a generative model for text to extract, like it's similar to clustering, but it gives you, for each document in a corpus, tells you how is this a mixture of different topics, and it's a completely unsupervised model. So you just give it a bunch of text, and you say, look for 100 topics, and then it gives you groups of these 100 topics, and which document belongs to which topics. There's also this graphical model, which, as Tim Hopper pointed out in a recent talk, is the worst way to explain any of this to anyone. Does anyone understand this without knowing what latent dirichlet allocation is? No? Yeah. Good. So we use online variational inference, if this means anything to anyone. So this is very fast. We also added a new optimization for logistic regression and rich regression called SAG. Here you can see a speed comparison. So it depends a little bit on which data set you're working on, but for very large data sets and very sparse data sets, this is very good. And it's basically faster than SGD always, and often faster than liblinear, which is the standard solver for logistic regression. It takes more RAM than SGD, but it's very fast. We also have a new solver for non-negative matrix factorization, which is like maybe factor 10 or something like that faster than the previous NMF in Scikit-Learn. We have also a new implementation of the Barnstead approximation for t-SNE. So t-SNE is now like a factor of 50 or 100 faster than it was before. We have also a cool thing. So I just mentioned this. So you can grid search over different preprocessings for your data if you use a function transformer. So function transformer creates a transformer for you from a given function. So maybe you want to use a linear model, and maybe you want to know some of the features you want to log, or some of the features you want to exp, or you want to compute sinus or anything. So function transformer, you give it any function, and it will create a transformer object from this that you can use in a pipeline. We also added a voting classifier, which is basically just a very simple ensemble. So you can give it some classifiers, and it'll average the probabilities.
Is this majority voting?
The question is this majority voting? There's voting hard and voting soft. Voting soft is argmax of the mean probabilities, and hard is majority. We added two scalars, which are called, so these are for preprocessing and scaling your data. The robust scalar, which uses robust statistics, so it uses the interquartile ranges to scale the data, which is more robust than using standard scalar if you have outliers. And we have max app scalar, which scales the maximum absolute value in your data. It's very helpful for sparse data. So before we had this min-max scalar, which scales data between 0 and 1. And you can't use that on sparse data because it shifts to 0. Basically, the only way to scale sparse data and not shift to 0 is this one. So it's like, we thought about long and hard how to scale sparse data, and we came up with this. I added links from the API back to the user guide. So each class now has a link here to the user guide, which helps you navigate the docs. Oh yeah, this was it before. Then for 0.18, one of the biggest things for 0.18 is we will have a complete rewrite of the Gaussian process. It will be much faster, much more rich. So you can build up arbitrary kernels and learn their parameters. This is the classical Mauna Loa dataset, or I think it's called CO2 dataset usually. And you can learn crazy kernels like this. We'll have neural networks. This will be just a very simple multi-layer perceptron that you can, like, if you think, oh, maybe a neural net will do better than my random forest, you can just replace the class name and try the neural net. I wouldn't use this for like serious big data neural net applications because we don't have GPU support. So this will be a lot slower than using things like Theano and Keras and TensorFlow. So if you're serious about deep learning, don't use this. We will also we'll have an improved cross-validation interface, but it's actually not that interesting. And we will have a faster PCA. So in the future, we will switch automatically between randomized PCA and non-randomized PCA, and it will like automatically set sweet parameters for you. And so this is runtime. This is how good the algorithm is, and you can see that sort of doing MNIST went from 25 seconds to somewhere around 0 seconds without like, oh no, it's here, sorry. Went to 10 seconds and it still is accurate. And labeled faces in the wild went from here to there and it's still pretty much as accurate. Buy my book. It'll come out June 2016, so relatively soon. It'll have no math, basically, so you don't need any linear algebra or probability theory, but it'll explain basically all of Scikit-Learn. This guy's called a hellbender. Thanks.
Hi, thanks for your talk. Do you have any plans of integrating Scikit-Learn with the distributed processing frameworks such as Spark or other frameworks?
So basically parallelizing the algorithm inside Scikit-Learn is near impossible. So you can rewrite them on Spark. That is what MLlib does. Or you can the thing that you can do is parallelizing things like grid search and cross-validation over the network. And there's the guys at Databricks, I guess, or the Spark people. They did this Spark sklearn, and it does that. So.
Thank you. I was wondering what the rationale is for writing a neural code from scratch instead of just wrapping one of the existing libraries.
It's not that hard to write it from scratch, and all the existing libraries either rely on Theano or TensorFlow, and Theano relies on CUDA, and that's basically... Yeah. So basically, nearly every time I tried to Theano on a machine, it failed. So trying to pip install Theano is tricky, and it's a very heavy dependency. And if you don't use GPUs, then you also don't gain much. I don't think it's... You can benchmark it, but I don't think it'll be faster. No more questions?
Okay, we are short on time anyways. No more questions. Let's thank Andreas again.